Hello, this is Celia Milena Ruben, and welcome to our presentation for Sound Classification Project. Here are some of the contents of our presentation. First, we're going to talk about the project and the objectives, then the dataset, our methodology, the EDA, the data preparation, building the data input pipeline, developing the deep learning model, the evaluation, and the problems and conclusions. Our project will focus on sound classification. Sound classification is one of the most used applications in audio deep learning. It is about learning how to classify sounds and predict the category of that sound. There are many applications to sound classification and detection for safety and security, as well as areas such as medicine and psychology. The problem approach for sound classification and detection requires using digital signal processing and machine learning techniques to extract useful features from the sound data and train models to classify and detect the different types of sounds. We will use the Urban Sound AK dataset, consisting of a corpus of sounds recorded in everyday city life. The sounds are of 10 different classes. Each sound sample is labeled with the class it belongs to. The dataset consists of two parts: audio files with 10 folders with each subfolder containing a number of audio samples, and metadata with information about each audio sample in the dataset. In order to achieve our objective, we have to proceed with the following methodology steps. These steps are: explore the dataset, pre-process data, build data input pipeline, build the model, train the model, model testing, and experimental testing. Exploratory data analysis is a crucial step in deep learning audio classification projects. It involves analyzing the statistical properties, distribution, and relationships within the audio dataset. Visualization techniques like histograms, scatter plots, and heat maps are used to identify patterns, trends, and outliers. The goal is to uncover any issues or anomalies that may impact the accuracy and performance of the deep learning model used for audio classification. By understanding the audio data, better decisions can be made regarding pre-processing steps and choice of deep learning models. The steps for conducting EDA in audio classification begin with importing the necessary libraries. The dataset, stored as a CSV file, is loaded, and the first 20 rows are displayed to gain an initial understanding of its contents. Two functions are defined to observe interesting aspects of the audio samples. One displays the audio file details on playback, while the other shows the audio spectrogram representation using short-time Fourier transform. A visualization of the waveform and spectrogram of a random audio sample from the dataset is presented. The EDA process concludes with the inspection of dataset labels on folds. The distribution of audio dataset labels is depicted using a horizontal bar graph, highlighting class distribution. Similarly, the distribution of dataset folds is displayed to understand how the data is divided. These visualizations help gain insights into the dataset's composition. In summary, EDA plays a vital role in deep learning audio classification by providing insights into class distribution, analyzing audio dataset characteristics, identifying potential issues, and exploring relationships between audio features. In the data preparation step, the data is pre-processed for later processing and analysis. The first step is the splitting of the dataset. To prepare the data for training the model, it is partitioned into the training and test set. As the audio recordings are given in folders, the data is already separated into subsets. The pre-existing folders will be used to generate the train test partitions. On the right, we can see the bar plots of class distribution by level of train, validation, and test set. This is useful to study class imbalance. As we can see, gunshots and car horns are the least frequent audios, and the rest of them are more balanced distributions. On the graph below, the sizes of the three sets can be seen, with around 62% of audios to be used for training and almost 19% for validation and testing, respectively. The following step is the audio classes labeling. The encoded labels are retrieved by mapping their names from the data frame. The 10 classes are air conditioner, car horn, children playing, dog bark, engine idling, gunshot, jackhammer, siren, and street music. The last step of the data preparation is the definition of the one-hot encoder. A one-hot encoder represents categorical data that converts each class into a binary vector with the position corresponding to the actual class is set to 1, while the other positions are 0. One-hot encoding the class labels for the training, validation, and test datasets will be useful for the creation of the input data pipeline. For the development of this work, two very important factors have been taken into account: execution speed and memory efficiency. The first step in building the input data pipeline was to normalize the length of our audio samples and calculate the audio embeddings using YAMNet as the transfer learning model. Why YAMNet? Because YAMNet is a pre-trained model that is commonly used to generate audio embeddings, due to its ease of classification of a large number of audios without the need for manual intervention. The second step was to build the input data pipeline, and for this we have used the TF Data API. Our dataset was constructed in such a way that we obtained a few pairs of embedded and labeled audio files. Together with our dataset and the TF Data API facilities, the input data pipeline was created. Some of these facilities are memory efficiency, efficient data loading and processing, flexible data manipulation, multiple data sources. In this way, we have obtained the training, validation, and testing dataset. One of the most commonly used neural networks for sound classification cases is the CNN. However, the LSTM can be also used for this task, as it has a number of advantages, such as sequence modeling, ability of handling data of different lengths, ability of learning long-term dependencies, bidirectional modeling. Bidirectional LSTMs can take into account both past and future information when modeling a sequence. Because of these advantages, in our case we have chosen a bidirectional LSTM, and the implementation has been in this way. First, an initializer was created and was used to initialize the weights of the neural network layers. Then, we created the input layer called audio. After that, the bidirectional LSTM layer was created with 128 hidden units. Finally, we computed the classification probabilities in the dense layer. Once trained the model with the data, we checked its performance on the unseen test data. Regarding metrics, first we can see the training history of the model, evaluated regarding accuracy and losses over the epochs. We can see the loss decreases in the training set with the epochs and stabilizes at a high value in the validation set. Meanwhile, the accuracy in the training set increases, and in the validation set, it stays at a low value. This indicates that the model is overfitting, not generalizing the new input data correctly. To solve this, regularization or dropout techniques can be applied, where the size of the training data can be increased. Next, there's the confusion matrix, which shows a high accuracy when classifying most unseen samples. However, there are some incorrectly classified samples that are confused with similar labels. This can be due to overlapping features in these classes or having audio recordings that contain features that represent various classes of audio. Finally, at the bottom right, we can see the ROC curve, which measures the overall effectiveness of our classifier. With the larger area under the curve, the better the classifier. In this case, the AUC is between 0.94 and 1, which indicates that our classifier is very good. In this first table, we can see the classification report with detailed information about the performance of the model, with precision, recall, F1 score, and support for each class. In general, there is a balanced number of samples of all classes, except for car horn and gunshot, in which the F1 score metric is useful. In general, we have quite high values except for air conditioner. In the right table, we can see the performance metrics that result in an average overall performance. The accuracy score of 0.8 indicates that the model classifies correctly about 80% of all samples. Once the performance of the model has been evaluated, we perform some practical experiments. In them, we introduce any audio, and our model predicts the class to which it belongs. For this, we defined a function that uses the pre-trained YAMNet model that extracts the vector representation of the audio. After this, the function uses the model to predict the class to which the audio belongs, returns the probabilities, and the class prediction is performed by identifying the class with the highest probability. Now we're going to show you the generation of predictions for 4 random samples. The class for this file was children playing, and the predicted class was children playing. The class of this file was dog bark, and the predicted class was drilling. The class of this file was siren, and the predicted class was siren. The class of this file was air conditioner, and the predicted class was air conditioner. We can see that the results are generally accurate, but they reflect what was observed for in the confusion matrix. The dog bark audio is classified as drilling, proving that some samples are misclassified because they share characteristics. During the development of our work, we encountered a few challenges. Firstly, there were limited audio samples in the car horn and gunshot classes. To address this, we divided the dataset based on folders. Secondly, we faced difficulties in building the input data pipeline. We treated the audio and labeling as numeric vectors using one-hot encoding. Finally, we observed phenomena like overfitting and misclassifications when evaluating the model's performance. However, we can say that according to the evaluation we have carried out, the performance of our model is very good. And this is it. This is the end of our presentation. Thank you so much for watching.